All right, so in this part of the screencast, this is part 2 of notes on the second section of chapter 1, 1.2, part 2. And we're going to talk about even and odd functions and about parent functions and transformations. So, even functions. Even functions are symmetric with the y-axis. In other words, they're a reflection over the y-axis. All right. So, for example, a parabola is an example of an even function. Imagine that. X squared, it has an even degree. Okay, an odd function is symmetric with the origin. All right. It is a rotation 180 degrees around the origin. If I can fit that on there. All right. So it's a rotation of 180 degrees around the origin. Now, for example, it might look like an x cubed. Imagine that again. Also has a odd degree. All right, so there's an actual definition for that you define with mathematics. And f of x equals y is even if f of the opposite of x is equal to f of x. And we'll talk about what the heck that means for every x on the domain. Okay, so it can't just be for some, it has to be for every x. All right, so f of x equals y is odd if f of negative x equals negative f of x. All right, so f of the opposite of x, I should say, is equal to the opposite of f of x, because if it's a negative x to begin with, then it's positive, so we should say opposite of. And again, for every x on the domain as well. All right, it has to be for every x, not just a few. Now, how do we tell? All right, and also it wants us to find zeros just so we can review how to do that. All right, so example. If I'm looking at this one, I'm looking at this and I go, oh, look at all those even numbers. Is it even? Probably is. All right, well, maybe, maybe not. So let's double check. Now, the definition is that it's even if f of the opposite of x is still equal to f of x. So how you check it is you take f and you put in the opposite of x. If you want to say negative x because it makes you happy, fine, whatever. Really, technically, you should say opposite of x. But, so we're going to go ahead and substitute in f of the opposite of x. And that's exactly what this notation right here means. It means put in the opposite of x everywhere you see an x. So right here, I'm going to replace that x with the opposite of x, or negative x if that makes you happy to say it that way. All right, so 2, and I'm putting in the opposite of x, and seeing if I simplify that, does it still turn out to be exactly what f of x was in the first place? So, now let's simplify. 2, well, if I do the opposite of x squared, or negative x squared, it's just x squared, because a negative times a negative makes a positive. So it's really just x squared. If you want to think of this as a coefficient of negative 1 in front of there, and then say, well, it's negative 1 squared, and then x squared, well, negative 1 squared is just 1, and then x squared is x squared, so it's another way to think about it. And the plus 4 doesn't need simplifying. So if I do f of the opposite of x, it gives me 2x squared plus 4. Lo and behold, that's exactly what f of x looks like. So f of the opposite of x equals f of x. So this is, in fact, even. My gut feeling that all those even numbers there were a hint. Good. It was a good instinct. All right. Now, I'm going to move this over a little bit so you have a little more room. Here we go. All right. Now, this guy, I'm looking at it, it looks pretty odd to me. So you always check odd and even by putting in the opposite of x and seeing if, even if you put in the opposite of an x, you get out what you started with, or do you get out the entire opposite of what you started with? So on this guy, you have to get the opposite of f of x out. So we're going to go ahead and substitute. Everywhere we see an x, we're going to change it to the opposite of x. Now, it's really, really important that you substitute in parentheses. So that's why I put parentheses here. So let's see. We got negative x cubed. Well, a negative x cubed times a negative x cubed times a negative x cubed. I said that badly. Negative x times a negative x times a negative x. 3 of those should give us a negative x cubed. Okay, if you want to think of it as negative 1 cubed and then x cubed, that's another way to think about it. You'd get a negative 1 and then an x cubed. All right, so I've got a minus right here, so that makes a plus x. Well, I definitely did not get my f of x back, okay? In fact, I got entirely the opposite of what I got back. So f of negative x, let's see if I'm going to try it this way and see if it's a little easier to see, but I'm going to take out the negative, or take out a negative 1 is another way to say that. And I'm going to keep my front part of my equation here. And so do you see now this inside the parentheses really is f of x? So I got negative f of x. Now I kind of just noticed right away it's entirely the opposite of what I had to begin with. So I got the opposite of f of x, or negative f of x, out. So you can kind of just notice there. So yeah, this is in fact odd, because that's the definition. If you put in negative x and you do some simplification and it turns out to be exactly opposite of what you started with, it's odd. Now, I saw this and said it's an odd power, and that's another odd power right here with the x, because that's x to the first. So an odd power minus an odd power, it's going to be odd. All right, so I kind of guessed it was going to be that to begin with. All right, I'm going to move it back so we can see this other item. Now, right here, I'm looking at that, and I'm going, this next one here, and I'm going, oh, yeah, definitely odd again, right? We got a 3, we got a 1. All right, so let me go ahead and let me put in, I'm going to change to red so it's a little different than the other ones. I'm going to put in the opposite of x, because that's how you check. If you put in the opposite of x and you get out what you started with, it's even. And if you put in the opposite of x and you get out the entire opposite, it's exactly negative of what you started with, then it's odd. And it can be neither, so let's find out. Let's see. Put in negative, opposite rather, of x. All right, that's the only x we have to substitute for. And then when I simplify that, just like the previous example, it should be negative x to the third, and I get a minus 1, because there's no simplifying to do there. Well, it's not what I started with. It's got this negative in front, so it's not quite that, but it isn't entirely the opposite, because this guy changed sign, but that guy didn't. So it's not negative f of x, or opposite of f of x. If I factor out that negative, it might be easier to see for those of you who are still going, huh? All right. So if I factor out that negative in front, boy, is that messy. Let me try to write that again so actually you can read it. All right. So if I factor out that negative in front, or factor out a negative 1 is actually more accurate at what we're doing, then you can see it's the opposite, and then that's not f of x. So it didn't turn out to be either rule. It's not even, because it's not equal to exactly f of x, but it's also not equal to the opposite of f of x. So this is neither. Now, remember I was saying even and odd degrees before? I want to talk about the degree of this constant part of the function. Well, that's really an x to the 0 part of the function. Okay, so the degree on that is 0. 0 is an even number. Okay, so a lot of people are under the misconception of thinking that 0 is a number that is neither even nor odd, and they're incorrect. Here is a little idea on how that is. You can just watch this. All right, so I'm going to put that back down in a second. All right, so if I am talking about even and odd, remember even is divisible by 2. So can I divide 0 by 2 exactly? I sure can. So it equals 0. So that's one reason it is even. Another reason it is even, let's just write out some numbers. Let's see, I'll start with 5, 4, 3, 2, 1, 0, negative 1, negative 2. It's good enough. Okay, odd. No one's going to argue with me there. Even, odd, even, odd. I'm skipping 0 because that's in question. This is definitely odd. That's definitely even. To keep in the pattern, that's an even number. Okay, so there's 2 reasons if you needed convincing. If you didn't need convincing, it was just extra information. All right. Uh-oh, it's not going to let me pull this back down. It is going to let me pull it back down. All right, so let me erase this mess. It won't let me do that. Oh, here it is. Okay. Oh, but it won't. Well, that's not nice. All right. So it's going to look really yucky over there. Sorry. All right. Now, this next one, my reasoning before with the odds and even degrees. Well, I've got an odd degree and an even degree. So I'm thinking right now it is a neither. It's not odd. It's not even. But we often have to prove things in math. So we're going to prove it. We're going to prove it to me and we're going to prove it to you. Okay. So we're going to go ahead and put in the opposite of x anywhere you see x. That's what you do anytime you substitute into a function. All right, so we're going to go ahead and do that. All right, so if I do negative x to the fifth, that's negative x to the fifth when I simplify. Again, you can think of it as negative 1 to the fifth and x to the fifth, or you can think of it as negative x times negative x times negative x times negative x times negative x, and that might help you see that it's going to be a negative. Now I'm going to do inside the parentheses first. There's nothing to do. Now I do exponents next. This is the order of operations, right? So this parentheses is going to be negative x squared, which makes it just plain x squared. That minus is still there. I've only done the parentheses and the exponents, okay? I brought that negative down with me. So really, this is negative x to the fifth minus x squared. All right, I'm looking at that and I'm saying, yep, I was right. It's neither because it didn't give me exactly f of x back. That's not f of x. It has a different sign right there. But it's not the opposite of f of x because not all the signs are different. If you need another step to see that, factor out the negative, and you can see that it's the opposite of this thing, but that's not f of x. All right, so it is, in fact, neither. Now, I said that we would do intercepts, but this is so crazy right now, we are so not going to add to the problem. All right. All right, so piecewise functions. Mr. McDermott and Mr. Trumbull and Mr. Constable also tell me this is something you did not do and have not done so much with. So we're probably going to have a little bit of extra practice on this. I'll post something else about piecewise functions for you to watch if you're really stuck. But don't make it harder than it is. It looks crazy. It's not so crazy if you get used to how it looks. So this right here is a piecewise function. Up at the top, this is the way it looks when you write it out. And this is the way it might look when you draw it, okay? So we're going to use the equation to get a graph, talk about domain and range, and we are going to use the graph to write an equation. All right, so piecewise function is exactly what it sounds like. It's a graph in pieces, okay? Now, wow, that's a terrible E. All right, forgive me. So this is f of x equals, and this bracket, which the computer didn't like making it big, but it's a bracket, an S bracket. You can make an S bracket easily if you don't know how, by making a backwards S or forwards S and then a backwards S. All right, so it just groups those together. It's saying f of x is these three pieces, and then it tells you, okay, we're going to graph negative x, which I hope you know how to graph, but you're only going to graph that where x is less than 0. Okay, and then you're going to graph x squared, which I think you also know how to graph, but you're only going to graph that the part of the graph that's between 0 and 1 for x. And then the last piece, you're only going to graph y equals or f of x equals 1, but you're only going to do that where x is bigger than 1. So let's go back and try each one of those. So I think you know how to, here we go, so you can see it a little better. I think you know how to graph Oh, it's not going to let me erase that little mark. So people who are really picky, sorry, that's going to bug the heck out of you. It's bugging the heck out of me already. All right, so you know how to graph y equals negative x. So really, if I just write this separately, you're graphing y equals negative x. That means you have a y-intercept of 0, right? And then you are going to go ahead and do a -1 slope. So it's going to look like this. Now, I'm not going to draw the other direction because I see already it says only graph this where x is less than 0. Well, x is less than 0 from the axis over to the left. So I'm just going to graph it on that side. Now, one thing we got to go back and fix right here is it's only where x is less than 0. I filled it in at 0. We should make an open circle there because it does not equal 0, right? It's only where it's less than 0, not equal to 0. So make that an open circle. Now, it's x squared. Okay, it looks like that parabola between 0 and 1. Well, all right, I'm going to scale my axes just a little bit. Probably should have let you know that beforehand. I'm going to do my axes every other one being a mark. So it's a little easier to see. -1, -2, etc. All right, so now between 0 and 1 for x, that's this little space right here, it's a parabola. So, you know, I would normally draw a parabola up, all the way going up, and all the way going over here. But we're not drawing the whole thing. We're only drawing that part between 0 and 1. So I'm going to just draw it, and I know it stops at 1 right there because, you know, we do it now. What happened here? At 0, we need to have an endpoint because it is equal to 0 for that parabola. And at 1, we need to have an endpoint, not an open circle, not an open interval, but a closed interval. And there you have it. Now, you can also do that on interval notation, by the way, and it could have been written that way. Like, for instance, this would have been in square brackets, and this would have been from -infinity, 0. I actually find that easier to understand. Your book uses the less than and equal to ones, and usually I think in piecewise it's more likely that it's written this way than the other. So, all right, and this one would be like 1, infinity because it goes on forever, all right? Open brackets, remember, always for infinity and negative infinity. All right, and so this third part just looks like y equals 1. Let me change to my brown so we have 3 different colors. Okay, so y equals 1 for that. Well, y equals 1 is a constant, like flat line. So at y equals 1, it's an open circle that we start with, but it's already closed, so we got it filled in, so it's all good. And we go y equals 1, and there it is. So this piecewise function has 3 pieces, 1, 2, and 3, and look, it has 3 equations, 1, 2, 3, over here, 1, 2, 3, that describe it. All right, now, let's write the equation for this graph in function notation. All right, so function notation, f of x, if you want to use g of x, I get really excited about f of x, I use it a lot. Have it. All right, so there's 2 pieces, so we're going to have 2 parts that we need to fill in. We need the equation, and we need the domain that part is on, all right? So let's see, I'm going to move it over a little bit because I feel like I don't have enough space for that. So this part right here, it goes from, we have to assume since they didn't give us a scale that it's -4 to +4. This part goes from -4 to +4, so that's my domain, so I'm going to write it that way. So x is between -4 and +4. I did not use less than or equal to signs because they're open circles. All right. Now, what the heck is the equation of that line? Well, it's a line, so y equals mx plus b. Now, I see right here, here's my b, yay. Okay, so I don't have to figure it out. It's 3, all right? So that b is 3, and the m we have to count. It doesn't matter which 2 points that you choose. I have 3 points labeled on there, so you could count between any combination of them. I'm going to choose this bottom one here up to this y-intercept just because. So I'm going to go 1, 2, 3 up, and 1, 2, 3, 4 to the right. So it's 3 up, so positive 3, and 3 to the right, so positive 4. It's 3/4 x. So my equation for that piece is y equals, now we already have the y equals, it's f of x equals 3/4 x plus 3. All right, so we can write the equation of that line, but it's not a line, it's a line segment. So you have to say, well, we're only looking at the line on this domain from -4 to 4. After that, it's not there, okay? Open circles because it is less than, not less than or equal to. Well, that's why it's less than or equal to, less than, excuse me. That's why it's less than, because it's open circles. It's not closed. It's not equal at those points. They're open. Now, this last one also is a line. Yay, okay. So it's a line, but it's actually a ray. It's only part of the line. So we need to come up with the equation and the domain. I actually like doing the domain first because that's easier for me. So it starts at 4, and it goes to infinity from there. There's an arrow, so we know it goes to infinity. If it was a closed circle, open circle, something, it would stop, but it keeps going. So it's everything bigger than 4. So the domain is x is bigger than 4. Actually, it's not just bigger than that. It's a closed circle, so it's equal to 4, so I'll add that in. So it's everything 4 and bigger is used for this little ray or part of a line. Now, the equation of the line, I don't know the b just by looking at it. We could figure it out with the 2 points with some of the strategies we've been using from the last section. I'm going to actually see if I can figure it out counting on my graph. It might be easier to go back and count. I don't know. We'll find out. You might have to figure it out, doing the 2 points, finding the slope. So if we can count on the graph, though, way easier. So I'm doing slope first because that looks a little easier. I can see that my slope is up 1, 2, 3 over 1, 2 to the right. So my slope for this guy is up 3, right 2. All right, so my slope is 3 divided by 2. All right, now, if I'm gonna just kind of think in my head about extending this line. All right, and if I had to extend the line all the way down to the y-axis, where would it end up? Well, I know my slope is positive 3 over 2, so I'm going to do the opposite to kind of see where it would go if it kept going down. So down 3, left 2, down 3, left 2. I end up right here. That's at -1, 2, 3, 4, 5, 6. So that's at -6. That would be my b if I had the whole line drawn. So that's the b for this line. It just never, you don't see it hit because you don't use that part of the line. So the b right there would be -6 if you extended the line. So that equation would be y equals, we already have the y equals, 3/2 x minus 6. And there you have that. So 2 parts of the graph, so there's 2 parts of the equation. You have to have the equation of the curve or line, whatever it is, as if it kept going. And then you also need the domain to say, well, it doesn't really keep going. It's only this little bit of it on that little part of the graph. This is the x's that you end up graphing it for. All right, next. All right, so we're going to graph this piecewise function. I want you guys to try it on your own. Just remember, it's 2 pieces, so you have to make 2 graphs. I'll explain it in a second, but I want you to pause and try it on your own and see if you can do it. All right, so 2 pieces, 2 parts of the graph. All right, so that first part of the graph is y equals 2x, right? And the other part of the graph is y equals -x squared plus 1. This part and that part, I don't want you, if it makes it easier to see it, to write it as 2 separate little things for a minute. I find this to look much less crazy with all the brackets and the commas and the less than's and the greater than's, and it just looks a lot easier to manage if you simplify it. Now, that first one's a line starting at the origin because y equals mx plus b, and then the slope is up to right 1. Now, I'm just going to imagine and have you imagine the line drawn in there, But really, we only need part of this line. We only need part of the line where x is less than 3, negative 3. So here's negative 3, negative 6 right here. That's on the line. Remember, we're imagining the line, the whole line. I find it easier to graph the whole thing than try to graph just the part that you're supposed to have. And then take off what you don't need. Pencil is key. All right, so we need to graph the part where it's less than negative 3. So less than is this way. Okay, so everything less than 3, you know, negative 4, negative 5, negative 6, negative 8. All right, that's the part less than negative 3. So we just drew part of that line. All right, I find it easier to try to graph it as if it were a whole line and then just either erase the part I don't need or draw in the part I need after that. My kiddo is having a great time out there. All right, now the other part is a parabola upside down. Upside down because of the negative in front. And this plus 1 afterwards, it makes it move up 1. So we're going to do a parabola. We're going to do up 1. Sorry, my thing won't let me erase those other little dots, so it's going to look a little crazy. So, but we know that only the red part there is the graph. So here's my vertex. I go up 1, and now I'm going to go down. Okay, it's going to be an upside down parabola because that negative out in front right there, that negative coefficient is doing that. Now, if you know parabolas, you can either make a table with your calculator or just graph. I always knew the pattern, so I know from the vertex I go out 1, and then I go up or down. Down this is the case because I'm upside down. Up or down 1. And then I go out 2 from the vertex, and that means I go down 4 because, you know, 2 squared is 4. 1 squared is 1, 2 squared is 4. Then I go out 3 from the vertex, and I go down 9, which would be at 8. And the same deal there. All right, so I kind of got the idea of the parabola. You can see the whole thing kind of forming, but I'm not going to draw it in, and I'd erase the other stuff when I'm done. But this is only where x is bigger than or equal to negative 2. So here's where it's negative 2. It's where it's bigger than or equal to, so I better do a closed circle because it does equal that negative 2 point. And it goes this direction because it's where it's bigger than negative 2. So I didn't need this other point over here. I don't think this little program will let me erase it. It won't. So here's my graph. Put together, it's this red part with the ray, open circle, because it's where it's less than negative 3. And this green part where it's closed circle, because it's greater than or equal to negative 2 for x. That's the domain that I'm going to draw it on. There you go. You just draw part of it, or if you're like me and I had to always just erase part of it when I was done. All right. All right, so now we're going to talk about transformations. I should have given you a note sheet, I guess you'd say, of all kinds of parent functions. All right, things that you start with and then shift from there. Now, just to remember from your Algebra 2 and Pre-Calc, vertical shifts are when you add outside the parentheses, I like to say, or outside of your function, whatever that parent function happens to be. Horizontal shifts, when you add inside the parentheses, and a reflection over the y-axis is when you make the whole thing negative. All right. So I want to do these little examples. All right, so if you refer to that parent sheet, the parent function of this is the parabola centered at 0, 0. Okay, so the parent function is this regular old parabola with no shifts. Well, this one has a plus 3 outside. That means it goes up 3. So up 3, all right, up 3, and then draw your parent function, all right? It's not perfect. Apologies. Now this guy, the parent function, all right, is 1 over x, okay? So that's my parent function. It looks like shoop, shoop, okay? So if I took that, it looks like instead of an x, what I have is an x minus 4. this is shifted 4, but this one is kind of opposite of what you think. Anything in parentheses is always opposite of what you think. So that minus 4 is actually to the right. Okay, to the right 4. So we take that whole little hyperbola and we move it to the right 4. 1, 2, 3, 4. All right, I'm going to draw the asymptotes in because it's easier to sketch this graph with the asymptotes. It didn't move up and down or any, so the asymptote is right there at 0 still. And there we go. You can double check me on your graphing calculator. And if I look at this guy, it's actually 2 shifts. Excuse me. We've got the minus 4 inside of it and the negative outside of it. But the parent function is just the square root of x. Remember, square root of x looks like this, sideways parabola. But this means I moved it right. Okay, the inside moves it left or right, which I didn't write down for you, but it moves it left and right. And this moves it up or down. All right. So that moves it right, and this will flip it upside down. All right. So instead of looking like our parent function does, it's going to be that parent function moved 4 over, but then flipped upside down. You can double check that on your graphing calculator, but it looks something like that. So remember your shifts and your parent functions to help you. And like I said, refer to that sheet to help you. All right, now combinations. So this has some combinations of transformations in it. This to me looks like the x to the third function, but I've added a 4 inside the parentheses, I've subtracted a 1 outside the parentheses, and I put a negative in front. So that means my x to the third, which by the way, remember, looks like this. You can refer to your little cheat sheet. It moves to the left 4. It moves down 1, and it's upside down. All right, so I take that whole thing and I move it down 1, left 4, 1, 2, 3, 4. Okay, and then I flip it upside down. So, all right, so I'm not perfect, but generally I've got my center point and I've got it generally there. All right, now remember absolute value functions. Our parent function there would be the absolute value of x. Okay, that's the basic function that's going on. And remember, that looks like a v. All right, so this means I went right 1. That means I went up 3. And this is actually have a leading coefficient. So that actually is another kind of transformation called a dilation. And that makes it half as tall. And I say it squishes it down, makes it fat. Okay, so we go right 1, up 3, 1, 2, 3. So my vertex is going to be there. But then I also kind of think of it as slope when it's absolute value. It's easier for me to think of it that way. It's up 1, right 2, up 1, right 2. And if you can see, it's making it a lot wider or fatter. Yep, I'll be right there, Alyssa. And there you have it. All right, the last thing we need to talk about is evaluating functions. So we're going to talk about several types of evaluating and doing some composite functions. Evaluating functions. This just says you read it g of 2. It does not mean g times 2. It looks kind of like a times. But when it's a function, it means take g and plug in 2 for x or whatever your independent variable is. So in our case, it's x. So it says take the g function, and anywhere you see an x, plug in a 2. Substitute in a 2 to be more appropriate in our math vocabulary. So then do the math. So 2 times 2 is 4, minus 6, negative 2, over 2, I get negative 1 when I do that. This one, where it says f of negative 1, says, okay, take the function f, and instead of x, anywhere you see an x, put in a negative 1. Really important to substitute in parentheses. All right, so when I do that, I get 1 plus 3 plus 1, that's 5. Okay, if you put this in your calculator and did not get 5, if you got 3, you forgot to put the -1 in parentheses, and it makes a difference. All right, now I'm going to do this one down here at the bottom with G next. All right, that says take G, and instead of X, you're going to put in 2M. So anywhere you see X, you're going to put a 2M. Okay, you're taking that G, and you're just changing the X to a 2M, so it looks like that. So now I get 4M minus 6 over 2M. And then we should probably simplify. So I happen to notice that I can factor out of both of those. Sorry, I'm moving it so much. I'm hoping it doesn't make you seasick there. All right, so I notice on the top I can factor out a 2. So I'm gonna. Okay, and on the bottom I also can factor out a 2. Okay, I'm basically just sticking parentheses in. But I think it's easier to see then that you can cancel those 2's. All right, common mistake is to cancel the 2 from here with either the 6 or the 4 and not do it to both. So remember, division is distributive just like multiplication, because division really is multiplication. It's multiplying by the reciprocal. All right, so my answer for this one, I didn't actually write it down, but it's really just that part. 2m minus 3 over m. You cannot cancel those m's because that m distributes. So if you cancel it from 1, you really need to write it as minus 3 over m, which is silly. So don't do that. You have to cancel it from both. You can't just cancel it from 1. Division distributes. All right, now we're going to put this into my f of x over here, my negative 3b. Here's my f of x. All right, so I've got f of x up there, and it says substitute in negative 3b. That means anywhere you see an x, you substitute in a negative 3b. Always put it in parentheses. My math teacher used to say, practice safe math, substitute in parentheses. All right, so there you go. Now, remember, that squared is for everything in there. So to simplify this, I have negative 3 squared, that's 9. Negative 3 squared is 9 positive. Okay, and then the b squared is just b squared. Now, that negative 3 times negative 3b is negative 3 times negative 3 is 9b. It doesn't distribute because there's no adding in there. When you multiply, you just multiply. All right? And then plus 1 after that. There are no like terms, so we're done. That's it. That's the best you got. You can't factor anything out. Even if you could, you don't need to. There you go. Now this last one is going to be for my AP students. We're going to talk about it at the end. Other students, if you want to listen to it, it certainly is a good precursor to when we talk about limits. All right, so now we need to talk about composite functions. Composite functions are when you do a limit inside a limit. So it's sometimes called g of f of x. By the way, you will also see it written like, not like that, but like that. Or sometimes without the x on it, okay? Or in this case, the x would be a 4. Okay, so that just means g of f of x. The g is outside, the f is inside. It means the same thing as this, except ours is a 4. So I like to work inside out, which you have to do. So really this means do the f of 4 first. So that means take f and put in 4. So I'm going to do that. I'm putting the g outside because I'm not doing the g part. I'm only doing the f part. So 4 squared minus 3 times 4 plus 1. All right, so I'm going to do the simplifying in there. That means 16 minus 12, that's 4, plus 1 is 5. 16 minus 12, that's 4, plus 1 is 5. So really now I need to do another step. Now it says do g of 5. So I'm going to go over to g, and I'm going to find wherever I see an x, and I'm going to change it up. It says substitute that to a 5. So I get 2 times 5 minus 6 all over 5. Do that math. 10 minus 6 is 4. I get 4/5. All right, and done. Now this last one, which is getting really squeezed out by my writing, I'm sorry, f of g of 0. So that I should do the inside first. So I'm going to do the g of 0 first, which means to find g and put in 0 wherever you see an x. All right? Now, I'm going to do that inside the parentheses stuff because, you know, parentheses, exponents, multiplication, division, blah, blah, blah. You do the order of operations. 2 times 0 is 0, minus 6 is negative 6, divide by 0. Problem, can't do it. Not possible. Can't divide by 0. Okay, all done.